Okay, we said that actually the Black-Scholes PD is connected to the heat equation or the so-called diffusion equation. And you can see here we have the time derivative on the left side of the diffusion equation, and on the right hand side we have the second order derivative in space, which is just our variable x. So how can this conversion from the Black-Scholes PD to the diffusion or heat equation can be achieved? So we need to define some change of variables. So you can see here is the Black-Scholes PD, and you want to get, somehow you want to transform this second order partial differential equation into the second, which is also a second order partial differential equation, and you want to convert this to the heat equation problem. So in order to do this, we need to do a few change of variables. So you can see we can get rid of this s and s squared terms, and we can make our original Black-Scholes PD equation dimensionless by setting these new variables. We can redefine these variables in terms of this x and tau. Okay. So basically, by defining this tau in this way, or you can see t is substituted with t minus tau and scaled by the sigma square over 2 term, actually we are reversing the time. Because remember, in the original Black-Scholes PD, we have a terminal condition. But in the heat equation, we want to make that terminal condition as an initial condition. So we can achieve that by subtracting this capital T minus a tau term. Okay. And also you can see that we can get rid of this s by scaling it in terms of the strike price k times e to the power x. Okay. So there are several steps in order to get our final result, but first each of these partial derivatives that we see here now must be computed in terms of our new variables, and here we can use the chain rule to achieve this. So you can start with the time derivative. So the time derivative, now since we are reversing the time, so we need to consider the chain rule in terms of our variable tau. Okay, and you can calculate this term first and multiply with the second partial derivative here, and you can see that the partial derivative of call option price with respect to tau, now this is going to be something in terms of the partial derivative of this v with respect to tau. Okay, and this partial derivative here is going to be equal to sigma square k divided by 2. And similarly, you can work out the partial derivative of the call option price with respect to the stock price s, and notice that now we are replacing s with k times e to the power x here. So that means we can use the partial derivative of the call option price with respect to x, right? And we are applying the chain rule just like in the first case, partial derivative of x with respect to the s. Okay, so you can see that now this first term here, that will be written in terms of v, and the second partial derivative here is going to be equal to e to the power minus x. Okay, and finally you can now work out the second derivative of the call price with respect to s, and we can write this in this form. And here again we are differentiating the result. In the first differentiation we get this result, and we substitute it here, and we can again apply the chain rule, and you can get the result here in terms of the product rule. So we are not going to go every single step. I think you can work out the calculus here on your own. Basically, once we convert each of these partial derivatives, you can go ahead and substitute these in the Black-Scholes PD, and if we rearrange these, basically we will get our equation 8 here. Okay, and here we have a constant. This k is defined in terms of 2r. This is the risk-free rate r, and divided by the volatility squared. okay? And also we need to convert our originally we had a terminal condition, as we said. Now it becomes an initial condition for this function v. There is one more step. Basically, now you can see we are getting close. So everything now is in terms of this v, x, and tau. Okay, but what we want to get is basically the heat or the diffusion equation. And remember that this is the form of the heat or the diffusion equation. Okay, so we still want to get rid of some extra terms here. So what was the extra term? So we have this additional term here. So in order to get rid of this, we need to do one more transformation. So we are letting this v to be equal to e to the power alpha x plus beta tau times another function u. So eventually, at the end, what we will get is going to be this, instead of v, actually we will use this u, and for the u we will get the exactly heat equation. So basically by doing this now trick, let's say, and by again substituting each of these partial derivatives with respect to tau and x for v, now we can write this equation 10. And finally, remember our goal is, finally, we want to get this u tau equals to uxx, which is this term. So everything else in this expression will be set equal to 0. So our goal is to find this alpha and beta such that at the end of the day, we will actually only be left with this these two terms, which gives us the heat equation that we are trying to achieve. So you can write these conditions, and here, as a result of these restrictions, as we said, all the other terms must be equal to 0. We can obtain the beta, and we have this choice. 0 is set equal to the 2 alpha k minus 1 term. So where does this 2 alpha k minus 1 comes? So you can see we have one partial derivative for x, okay, and another partial derivative of x is here. So it is 2 alpha plus k minus 1. So we need to set this equal to 0, otherwise it doesn't disappear, right? And also you can see the first condition here. We have this beta u term, right? We have this alpha square u term, and we have this k minus 1 times alpha u and minus k times u terms. So these are also again u terms here, you can see. So it is represented in the first equation here. So basically we can solve these equations for, we have two equations and two unknowns here, so you can solve it for alpha and beta. So that will give you these two results. And then you can go back and substitute everything in terms of our definition for V. And finally, this gives us the heat equation that we were trying to get. Okay. So this completes our connection between the Black-Scholes PD versus the heat equation. So you can work out each of these steps a bit more detailed and convince yourself that actually Black-Scholes PD can be converted to the heat equation.